Welcome. This is Coach Dorf. Today we're going to talk about section 4.1 that deals with the absolute max and min values of functions. So first, to discuss this topic, we need to look at some definitions. What is absolute max? What's absolute min? What's a local max? And what's a local min? And we'll talk about this by doing some examples. So first, here on the left, we have a graph that's in red. An absolute max means that it is the largest y value of the function throughout the whole domain of the function. So if you have an absolute max, there's no other y values on the graph that are larger than it. An absolute min is the same idea, except that it's the smallest y value for the entire graph of the function. So if we look at our red graph here, we'll see that there is no absolute max and no absolute min because of the arrows at the end of the curve. And that means that the graph is going to go on forever, getting larger and larger on the right side and getting smaller and smaller on the left side. So we have no absolute max because this right side gets larger and larger, and there's no absolute min because the left side goes on getting smaller and smaller. Now, what's a local max and a local min? Well, a local max means that if I just take a snapshot close up a part of the graph, that there's a point there in that snapshot where it's always the largest value for everything in that snapshot. Another way of thinking about that is if I draw a circle around a part, and in that green circle there is a value on the curve, we'll just say right about there, that is the largest value of the graph inside that circle. And in that case, that's known as a local max. And likewise, if I can do a green circle or whatever color circle we want to do, I'll do green here. If there's a point there where that's the smallest value, let me redo that line here. That's the smallest value. That's going to be a local min. So in that second green circle, there's no point on the curve that's smaller than that blue circle, that blue dot. So that's a local max and local min values. Now, what about if we have a function that has endpoints, like in this purple one? Well, the first thing to note that it's customary to say that there are no local max or mins at endpoints. So in other words, if I look at that point, it's not a local min, and that is also not a local min. However, we could have absolute max and mins when we have endpoints, and that's what's going to happen here. If I use blue here, this point here is going to be an absolute min because I draw the circle around it, and the smallest value on the curve is inside that circle, that purple point, and even if I didn't draw the circle, it is the smallest point, minimum value for the curve. All right. On the other hand, if I have this point here, this is not an absolute min because the purple point on the right side is not as low as the purple point on the left side. So the one on the left side is an absolute min, but the one on the right is not an absolute min. And as we said earlier here, there's no local max or mins at endpoints, so we don't have to worry about that. There is one other point that's of interest here, and that's going to be in the circle here. We'll just have this point here, and that's going to give us a local max, which is also going to be a absolute max. It's an absolute max because there's no point on the purple curve that's larger than it on the entire purple curve. And it's also a local max because if I draw that green circle around it, there's no points inside that green circle on the purple curve that's also larger than this. So something can be both a local max and an absolute max, but it doesn't have to be. All right, let's go to the last example, the green one over here. All right, so what do we know about at this point here? Well, it's going to be an absolute max. Is it a local max? No, because of the fact that there's no local max at endpoints. All right. What else do we see? Well, we have this point here. All right. That's going to be a local min. Is it an absolute min? No, because there's other points on the green curve that have a lower value than that one. What about this point here? Well, that's going to be a local max. Is it an absolute max? No, because it's not as large as the green point that's circled in the purple area. And let's see another color. Okay, find colors that will work. Let's see if this orange one will work right there. What about that point? Well, it's a local min because everything in the circle, in the orange circle, um, greater than that orange point, but it's also an absolute min because it's the lowest point on the green curve of every green point there is. And finally, if we look at this point over here, what do we know about it? Nothing. So this is not a local max and not an absolute max or min. It's not absolute because there are green points that are above it and below it. So it's not an absolute max or min. And it's not a local max or min because it's at an endpoint. All right. So let's add a clicker problem here. Put this one to come up. Okay. So problem. Let's see what we can get from here. So here we have this graph. Now this is a little bit different type of graph. Notice that at x equals 0, we have y value. We go up on the graph and we get near 4, but there's an open circle there. When x is 0, there's an open circle at y equals 4. Also at x equals 1, if I look at the curve, there's an open circle at x equals 1 and y equals 2, but there's a closed circle at x equals 1 and y equals 3/2 or 1.5. And everything else is, all the other circles are filled in. So what can we tell about this function in terms of absolute max and mins? All right. Well, what is the absolute max on this? Well, some people would say it's 4, but that's not correct. All right, because that 4 value could potentially happen when x is 0. So f of 0, you look at that, you near 4, but you don't have 4 because it's an open circle. So there is no max value on this function, all right? Because there's that open circle at x equals 0 and y equals 4. And if I take anything less than that, I can get really, really close to 4, but not get 4. So like if I were to say, well, maybe there's an absolute max at 3.9, well, then I would say, well, 3.99 is on the graph, and that's larger than 3.9, so 3.9 can't be an absolute max. And then someone could say, well, what about 3.99? And that's larger than 3.9, and that's true, but it's not as large as 3.999, which is also, did I get that right? 3.999, yeah, which is a graph. And you can just keep playing this game forever, and you can get really, really close to 4, but you can't get something, you can't find a specific number that's less than 4, that there isn't a number larger than it. And we can't pick 4 because there's an open circle of 4. So there's no absolute max value. What about absolute min value? Well, some people would say that that's 2, because if you look in the curve here, when x is 3, when x is 2, then there is the point y equals 2 that's on the curve, and that's a filled-in circle. But that's not the absolute minimum value of the function. The absolute minimum of the function occurs when x is 1, and we have that y is 1.5 or 3/2. Okay, even though that's not a connected part of the graph, it's still part of the graph. So in this example, there's no absolute max value, but there is absolute min value, and that occurs at x equals 1, and the min value is 3/2. So letter C is the correct answer for this one. Okay. And this point that I want to make here too, and that is note the difference between the x value. This is where the max min, let me write that, where the max min occurs, and the y value, which is the value of the function at x, where the max min occurs. Okay, so there's a between the y value and the x value. They often say the max min occurs at x, and the value of the function, or the value of the max min, occurs at the y. All right. To find max or min values, we of a function first find a thing called the critical numbers of the function. All right, so we have a little definition here. A critical number of function f is a number c in the domain of f for which f prime of c equals 0 or f prime of c does not exist. So I think it would be good to go through an example of this. So let's look at an example. Up here, let's f of x cubed minus 3/2 x squared minus 6x plus 2. There's my function, and I want to find the critical numbers. Find the critical numbers. Well, to do that, I'm going to take the derivative. So the first thing I do is take the derivative. The derivative of this, I just use the power rule, and I get 3x squared minus 3x minus 6. And I want to set that equal to 0. Okay, so now I factor this. What do I do to factor this? Well, anytime I factor it, I look to see if there's anything in common. There is something in common here. It's a 3. So I'm going to factor out the 3, and I'm left with x squared minus x minus 6 equals 0. And then I'm going to factor what's inside the parentheses. When I do that, I get an x and an x. The two numbers multiply to be -6, and they add to be -1x. So that's going to be -2 and a +1. Wait a second. Oh, I didn't do that right here. Let me go back here. I made a mistake. When I factored that, all right, I should have a 2 here. Right. Okay. So then I get this 3 times x minus 2 and x plus 1. Okay. So what does it tell me about x? X equals 2 or -1, and these are then the critical numbers. And let's look at a graph on Desmos for this. So let's see, pull this up. Okay, here we are on Desmos, and I'm looking at this function that we have, x cubed minus 3/2, x squared minus 6x plus 2, the function I started with. And here's the graph of that function. Notice, recall that we had the critical numbers at 2 and x equals 2 and x equals -1. So at x equals 2, we're right here, x equals 2. We have 2 comma -8, and that is a local min. So there's a local min at x equals 2, and its value is y equals -8. Then at the other critical number, x equals 1, we have this, which is a local max. So there's a local max at x equals -1, and its value, the y value of the local max, is 5.5 or 11/2. All right, so going back to my iPad, let's do another example. That's maybe a little bit more complicated. All right, find the critical numbers of function f of x equals x to the 3/5 times 4 minus x. Okay. This one's going to be more complicated because it has a fractional exponent, but I think it's a good example for you to see to help you know how to do these problems. All right, so the first thing I would do is multiply the x to the 3/5 through to everything that's inside the parentheses. So that's going to give me 4x to the 3/5 minus x, and now I'm going to add 1. So I'm going to have an exponent of 3/5 plus 1. So 3/5 plus 1, this exponent right here is 3/5 plus 1, because the exponent on the original problem, inside the parentheses, it was 4 minus x to the 1. So I'm adding 1 to the 3/5 when I multiply those together. And when I do that, you get a denominator and you get 8/5. So right here, this is 8/5. All right, so now I'm going to take the derivative. So I just do the power rule. I'm going to get 4 times 3/5 x, and now I'm going to subtract 1 from 3/5. And I'm going to get -2/5 for that exponent. And by the power rule in the second term, I have 8/5 out front, x, and now I subtract 1 from 8/5, and I get 3/5. And we want that equal to 0 in order to find the critical number. Now, I can simplify this a little bit. The x at 12/5 x to -2/5 minus 8/5 x to the 3/5. Okay, that's going to equal, I'm going to erase this equal, I don't need that there. Okay, now what do I do here? That looks really complicated, and it is complicated. So what I'm going to do is I'm going to factor out what they have in common. So in the fractions, I have a 12/5 and an 8/5. So I'm going to factor out a 4/5. And I'm going to do that because then I will have just then I'll have no fractions in front of the x terms. Okay, oops, I don't want to do that yet. All right, and then I want to factor out some x part. So what's the exponent I want to factor out? Well, I look at my two fractional exponents and I want to factor out the smallest exponent on it. This is what you usually do when you factor something out, right? If I just go off here to the side, let's suppose I had 3x to the 4th minus 9x cubed. If I wanted to factor that, I'd first factor out the 3, and then I would say, how many x's do I factor out? Well, I've got 4 in the front and 3 in the second term, so I factor out 3. So in essence, what you're doing is you're taking the smallest exponent there, and that's what you're taking out. You have an exponent of 4 and you have an exponent of 3, you take out the smallest one. And then when you're done with that, you're left with something like this. Okay, that was just an example, but it doesn't, okay, we're going to use example now to apply it to this problem that we're doing here, to factoring this that I'm circling in red. Okay, so we've taken out 4/5. So we look now at the exponents. I have x to the negative 2/5 and I have x to the 3/5. Which is a smaller number? Well, negative 2/5. It's a negative number and 3/5 is a positive number. So I'm going to take out x to the negative 2/5, a smaller number. What do I have left after I take that out? Well, in the first expression, which I'll color here in purple, I've taken out 4/5 x to the negative 2/5. I'm left with a 3, because 3 times 4/5 will give me a 12/5, and I've already taken out x to the negative 2/5. All right, how about the second term, which I will circle in blue? When I take out, what's left after I've factored out the 4/5 x to the negative 2/5? Well, I'm going to have a 2. Well, let me do that in black so I'm consistent here. And I'll have an x to the first power. Whenever you have a problem like this, if you've done it this way, you will always have, in this course, your x will to a non-fractional power. That's the way it just works out on these types of problems. Okay, and I can check this now. If I use green here, I look at this negative 2/5 and this 1. If I add those together, negative 2/5 plus 1, I'm going to get the 3/5 that I started with over here. So that makes sense that works. Okay, so what's the step? Well, I'm going to rewrite this. I've got, inside the parentheses, I've got 3 minus 2x over, and then I've got a 4/5 out front. And in the bottom, I'm going to have x to the positive 2/5 power. And I want that to equal 0. All right, so for a critical number, we want to consider the derivative equal to 0. So when does that derivative equal 0? Well, that is when the numerator is equal to 0. I don't have to worry about the 4/5 out front, just need to worry about the things that have x's in it. So I have 3 minus 2x equals 0. And if I solve for x, get negative 2x equals negative 3, divide by negative 2, and I get x equals 3/2. So there's a critical number. But I also have a critical number if the derivative does not exist. And where does the derivative not exist? Well, that's when the denominator equals 0. So that's when the denominator equals 0, because I have a rational expression, a fraction. And when does x to the 2/5 equal 0? That means that x equals 0. So that's also a critical number. So I have two critical numbers here, x at halves and x at equal to 0. And let's again look at Desmos here and see what this function looks like. Okay, so here's the graph of the function. The original function had x to the 3/5, just checking x to the 3/5 times parentheses 4 minus x. There's the graph. So what's happening at x at the critical number x equals 3/2? Well, x equals 3/2 is here. And what do I have for the function? 3/2 is the same as 1.5. I have a local max there, which is also an absolute max from what I can tell in this function. All right, what about at x equals 0? We have this. What's happening here? Well, that's the point 0, 0, and that is a tangent. So at x equals, there's a local max and an absolute max. I'm running this on the iPad. You can't see it yet, but you'll see it when we get back. And at x equals 0, the derivative does not exist because it is vertical tangent. Remember, a vertical tangent means that if I try to draw the here in Desmos, if I try to draw the tangent line, it would be going exactly up and down. It would be that y-axis. That would be the tangent line. And what's the slope of that? Well, it would be infinity, and we can't have that. So that's why the derivative doesn't exist at that point. All right, going back to my iPad here, you can see where I wrote this down here. So at x equals 3/2, there's a local max and absolute max. And at x equals 0, the derivative does not exist because it's a vertical tangent. All right, let me just one thing here. Suppose my function is f of x equals 1 over x. That would mean the derivative would be -1 over x squared. But 0, should say equaling 0, is not a critical number because 0 is not in the domain of the original function. So in order for, if the derivative equals 0 at a point, it's only a critical number if that original x value was in the domain of the original function. If I go back to my previous example here, which I will here in red, okay, is x equals 0 in the domain? Yes, I don't have any fraction there, no rational expression, no 0 in the denominator. And the x to the 3/5 out front is not a square root or a 4th root or a 6th root, it's a 5th root. So it's okay for x to equal 0. In fact, even if it was a square root, it could equal 0. But because the derivative we saw here, the derivative not exist, x equals 0, that's why it was a critical number. Unlike the example that we did here, where the derivative equals 0 at x equals 0, but x0 is not in the domain. All right. Also, let me point out that the fact if f has a local max or min value at x equals c, then c is a critical number. However, the inverse of that doesn't work. If c is a critical number, if I go in the opposite direction of the statement I just wrote, if it's a critical number of f, then we don't know if there is a local max or min at x equals c. And the common example of that, I hope you remember that, is f of x equals x cubed. The graph of that looks like this, all right? And if I take the derivative of this is going to be 3x squared, and that equals 0, suggests that it tells us that x equals 0 is a critical number, all right? But what happens at x equals 0? It's not a local max or min, it's neither, okay? It'll turn out, we'll call this a thing called the inflection point, but we'll talk about that later on. Okay, the last idea we have to discuss here is following. Think of this as a goal. Sometimes you'll be asked to find absolute max min values of a continuous function on a closed interval. So this kind of relates back to the very beginning of the discussion. So let me go back up here, the very beginning, my slides. Remember the purple graph in the middle and the green graph on the right, they had end to them. They didn't go on for infinity. So they had endpoints. There's no or max mins at the endpoints, all right? But you can find absolute max or mins. We are now dealing with that type of situation. So we're going to be finding absolute max mins of a continuous function on a closed interval. So there's going to be endpoints. All right, how do we do this? You do the following steps. First, you find the critical numbers on that closed interval. And then next, we're going to find f of c, the value of f of c for all critical numbers. And then finally, next then would find the value of f of a. So that's one m, and evaluate the function at the other f point, f of b. Then the largest value in 2 and 3, is the absolute max, and the smallest value in 2 and 3 is the absolute min. So let me do an example of this. All right, let's find, pull up a sheet here. Okay, the absolute value of the function f of x equal x cubed minus 3x squared plus 1 on the interval from 0 to 3. All right, so we're going to follow this approach that's listed at these 4 steps. So the first thing I do, number 1, find the critical numbers. So that means I take the derivative of f. So that's going to be 3x squared minus 6x. I set that equal to 0. And now I want to find when does that equal 0. So I'm going to factor out a 3 and an x, and I'm left with 3x outside times parentheses x minus 2 equals 0. So that means x equals 0 or 2, and these are the critical numbers. Okay, the second step is I want to find f of c, the value of the function at all of these. So I'm going to do f of 0. And so I go back to the original function. So let me write it this way. Let me write down the original function. So f of x equals x cubed minus 3x squared plus 1. So I look at that, and now I'm going to do f of the first critical number. So I put 0 in there, and I get 0 cubed minus 3 times 0 squared plus 1, which equals 1. And then I also look at f of 2. I put that in there, and I get 2 cubed minus 3 times 2 squared plus 1. So that's 8 minus, I've got 2, which is 4. 3 times 4 is 12. So I have minus 12 plus 1. And that looks like negative 3. Okay, so that's step 2. By the way, I need to make sure that those critical numbers are in the interval from 0 to 3. And they both are. 0 is in there, and 2 is in the interval from 0 to 3. If they're not, then I just don't use that point. And then next I look at f at the intervals. So I've got the interval from 0 to 3. So this means a is 0 and b is 3. So now I look at f of a, which is f of 0, which we already did, and we saw that was 1. And then I do f of b, which is f of 3. So I plug 3 into the equation, and I get 3 cubed minus 3 times 3 squared plus 1, and that's going to turn out to be 0. So, sorry, that's going to be 1. Okay, so the values I have are 1, 1, and negative 3, and 1. So the absolute min occurs at x equals 2, and the absolute min is f of 2 equaling negative 3. Okay. Again, be careful how you phrase, see how I phrase that. The min occurs at x equals 2, but the absolute min value is negative 3. All right, that should help you with the homework. Hope that helps you, and have a good day.